Hi there and welcome back to Triplicate, and moving on yet again with our still as yet unnamed radical synthesizer design. And we have established it will not have a piano style black and white keyboard, will not have any MIDI, it will not have conventional oscillators, filters, etc, etc, and it will have some serious attitude. So we've decided how we're going to play it without a keyboard. So taking our lead from the hurdy-gurdy, we have a turntable, and that will drive the sound in the way a bow does on a violin, or the breath does on a wind instrument, or the handle does on a hurdy-gurdy. And we will control the pitch of our notes by these three strings, initially three because I built this for a previous project. And we've got that far, and we've got, you can see a nucleo hanging off this. We've got this kind of working. So in this video we're going to change tack a bit on the project and start looking at how we actually make some sound without resorting to oscillators and envelopes and so forth. So I've always wondered why acoustic instruments sound so much more alive, dynamic, natural than synthesizers, which can sound flat and harsh. I'm not sure I'm thinking of the right words here, but hopefully you know what I mean. So what I am proposing to do for the sound generation system of our synthesizer is in some way take a lead from how acoustic instruments make their sound. Now I need to stress most strongly at this point that we are not under any circumstances actually going to attempt to model or recreate any existing instrument. We are making a synthesizer. We're just going to try and take the way an acoustic instrument makes sound and adapt that to our needs. Okay, to hear a sound, something needs to be oscillating in the hundreds and thousands of hertz mark, which to us humans, no, we can't do that. More than a few hertz. Now, if you're a bee or a fly, you probably could play a tune on your wings, but we're not. So we need to come up with something different to make our musical instrument. So we have to somehow get some sort of sound, some sort of oscillation, we might call it, from things like blowing air through a small hole or dragging a bow along a string, as in a violin, and a hurdy-gurdy works in the same way, if you were wondering. Whereas of course in electronics and in software we can make an oscillator, just something that makes a repetitive waveform forever and a day. Now in an instrument, a stringed or a wind instrument, the sound comes from something that's resonating. In this guy, the air is resonating in the pipe. In a violin, the string is resonating, and we also have some magic thing which we will look at that actually triggers the oscillation. On the other hand, in like an electronic oscillator or a software oscillator, every cycle is the same and the harmonics are all fixed hard into the cycle, so we have a ramp wave over and over again, whereas in our physical resonance system, as in the pipe here, the harmonics can exist independently in the pipe, and they don't all have to exist at the same time. One of them can drop out or be boosted, and they don't have to be in the same phase all the time, which is I believe why this sounds so much more interesting. Well, not this because it's a cheapo whistle, but in general acoustic instruments sound so much more interesting because the harmonic content is constantly varying and the phase and the amplitude of the harmonics is constantly shifting, whereas in an oscillator they're absolutely fixed. Also, again, in this there will be a noise content, and we will be blowing a constant stream of air into the end here, and there will also be a noise content, and specifically in a flute. Flute being the best example, the breathy sound of a flute is the noise that is being injected into the system with the constant air pressure from the player's mouth. Okay, so here we have a note played on our penny whistle. So let's just listen to a short section of this. Sorry about the loop points. Okay, and let's look at the spectrum of it. And you can see that some of the harmonics, like this one, the level is sort of fairly variable and random, and you can also see that there is noise in between the harmonics, so this waveform is not entirely harmonic. There is a noise element to it, as I was describing just now. So now let us take a spectrum analysis of this, and we get that. So I took the numbers of the harmonics, the levels of the harmonics and the frequency out of that, and I generated a tone with the same spectrum but just a continuous tone as if it was generated by an oscillator, which sounds like this. Now, interestingly, when it starts for the first half seconds it does almost sound like our penny whistle, and then it just locks into that continuous tone of an oscillator. So that's what I'm saying, why we want to get away from the oscillator and to a more natural way of generating tones. And if we look at the spectrum of this, you can see I've only generated the 5 harmonics, but you can see the harmonics are dead constant and there is nothing in between them. So how actually does something like this work? I'm blowing down that end a constant stream of air, yet something is creating an oscillation. Now we know this bit is a tube, and a tube of a column of air, a pipe full of air will resonate because something is making it resonate. Now if I blow down this end, absolutely nothing happens, but if I blow down this end, we get a sound. So it must be something to do with what's going on in this little guy here. So this is a diagram for a recorder, and what we see is that the air jet that you blow in can either go above this edge here called labian or below, and it is sort of semi-stable in both these states, and I don't propose to go into the physics of what's going on here because it's complicated and not very helpful to what we're trying to do. But the basic thing is to remember that the system has 2 semi-stable states. Okay, and the situation for a violin string or any sort of bowed instrument string is a bit simpler. So here we have a piece of wood pulled by a piece of elastic and weighed down by a multimeter. Not working brilliant, but you'll see it sticks. There is what's called stiction and friction. It sticks till you get a certain amount of force on it, and then it starts moving, and then the resistance is a lot less, so it can move a certain distance till the force drops below a certain level, and then it will stop again and stick again. So let's see if I can get, we try a bit longer elastic. Worked better yesterday. Sticking, friction. Okay, so let's have a look at this. Let's have a look at how this works on a bowed instrument. So here we have a string, which is a piece of elastic, which you might recognise from the previous shot, and here we have a piece of wood which is acting as the bow, and this is not going to work really. I'm just going to hold the string. So what happens is the string sticks with the bow by stiction. So the bow is moving that way and the string sticks onto it until it gets to a certain point where the string, the further out the string gets, the more it pulls back, and at this point the pull on the string overcomes the stiction and the string starts moving that way as the bow still's moving this way, but the friction is a lot less. So the string will swing back to here and then start moving back and catch up with the bow, and it's back to stiction, and then I have to move my bow back and run out of space. Again it will go stiction till the string breaks loose and slides back, and etc, etc. So in the bowed instrument we have the two stable states, stiction and friction. Now at this point we could start to write some computer algorithms to try and I suppose mimic this behaviour, but I thought we do too much on the computer really. I mean, the nature of the projects we do means we can't avoid it, but I thought we'd just do a little gratuitous electronic mucking around at this point. Okay, so there is an electronic component that exhibits this kind of behaviour, and that is a neon. And I was inspired to do this little muck around by a Fran Blanche video, which I'll leave a link to, in which case you use a number of neons linked together to make an interesting sort of flashing neon sculpture. But as you can see here, the neon is basically two little electrodes in a glass envelope which is filled, not surprisingly, with the inert gas neon. Now I'm not proposing to go into the physics and detailed behaviour of how a neon works, but it basically works like this. So if we have voltage here and current here, if we start at no volts we have no current, and if we increase the voltage, basically the neon gas acts as a pretty much perfect insulator, and we get no current till we get up to about 90 volts, in which case we get an arc forming between the two electrodes. The neon turns to a plasma and basically has an impedance of very little. So this very quickly goes across somewhere to here with a high current and a very small voltage. And now if we reduce the voltage, the current stays high till the arc goes out, and then the current drops to zero. So we have our two-state system. We have our high impedance system and our low impedance system. So we can make an oscillator out of that. Okay, so here's our oscillator using a neon. So here this is an oscillator, remember, that doesn't use any active semiconductor devices. So what have we got here? Well, I don't have a 100-volt power supply. So I've got to run it off the mains, so absolute health and safety here. So these two resistors half the mains voltage, just to try and keep things within sane ranges, and that diode is a half-wave rectifier, so that capacitor will charge up to, I don't know, 150 volts or so, we'll see. Right, so that is just the power supply really. So what happens is, well, imagine when this capacitor is discharged, the neon will be high impedance, there'll be no voltage across it, so this capacitor will charge up, and with it the voltage will increase across the neon to the point it gets to 90 volts, and the neon will turn on and be pretty much short circuit at that point. So the capacitor will discharge through this resistor, which is just to limit the current through the neon, until there isn't enough current going through it any more to maintain the plasma, and the neon will then go out and the capacitor will start charging up again. And you may be looking at this thinking that's a slightly odd way to draw that circuit. Well, there's a very good reason for that, and that is this. Okay, so here we have a scrap piece of floorboard filled with spider web, and on top of it we have printed out the circuit I just showed you, printed on adhesive backed paper and stuck to it. And here I have a big load of steel panel pins which are conveniently plated with I guess zinc, but anyway you can solder to it. So all I propose to do is hammer a bunch of these into these where these dots are, and I can just solder the components on there where they're shown on the paper, plus the fact they're all nicely spaced out with big air gaps for relatively high voltages, higher than triplicate normally deals with. Okay, so here she is, with my nails in on the circuit, so I can solder to them some capacitors, some diodes for there, got some, well, they're 1 meg I think resistors for there, got some neons, 100k resistors. So I am going to get my soldering iron and solder some of these on here, and I'm not going to burden you with watching me solder them on here because it's hardly high tech. And then when I've soldered them on, we'll fire it up and see how it goes. Okay, everything with the neon connected, and the mains plug definitely not plugged in. In the interest of my continued living. So here we go. Let's just tack this neon on and see how it goes. There we go, one side of the neon. Come on. Around there. How are we doing? Other side of the neon. And that should be it. So, are we going to plug it in and see what it does? Okay, here's the mains plug. In she goes. Right, stand back. Okay, so keep my hands well away from this thing. It's not the safest thing I've ever built. I'm hoping that you can see that the little neon is glowing faintly all the time. So this tells us something interesting about this kind of system, is that you can configure it to be stable. And if that was our musical instrument, then it wouldn't be making a noise. So what's happening is that at this very low brightness, the current flowing through the neon is low and balances the current coming in through the 1 meg resistor here, so it's stable. So what I will do is get another 100k resistor and solder it across there. Okay, and I've discharged these capacitors, so I'm not going to give myself a shock off it. There's my resistor. Okay, that's tacked across there. So, shall we zoom in? To about there, grab the plug it in, and did you see that? Fire it up again. Oh, and there we go, it's blinking. I guess 2/3 of a second or so. Get a better. Okay, so that works. That is oscillating, and obviously not at audio, but that capacitor there, if that was a lot smaller, it probably would blink at audio speeds. I don't know. Anyway, we're not interested in neons, so we are going to try and build a software oscillator that works on the same principle. Okay, so here is our little software model of what's going on here. Well, okay, let's work up. We are looking for VC, that is the output voltage we are going to take as the output of our oscillator. So neon, that's neon VC here. And from Q equals CV we get I over C equals delta V, kind of differentiating it. Again, I'm not going to go into this in huge detail at this point. So we can calculate our next VC, our voltage out, from the last one, and IC. And we can calculate IC, which is IR, the current here, minus IC, the current here. And IR here is simply the voltage across our charge divided by the value of our charge, and we are assuming the neon is either hard on or hard off, and turns on when the voltage gets up to a certain voltage and turns off when the voltage gets down to a certain voltage. This is a very much simplified model, but it'll do for us. So if the voltage is off, I neon is 0, and if the voltage is on, I neon is simply the voltage across the neon divided by R flash, that resistor there. Okay, shall we run this up and see what it does? If we look here, for now neon, the capacitor neon C has a fixed value, so we will try that for size and see what happens. Okay, so that's done. Doesn't print anything out or anything, so we will get rid of that. And let's look at what we've got there. So, we'll play that. Well, it's oscillating, and if we look in there, we can see the capacitor charging up slowly, and the neon turns on, discharges quickly, neon turns off, capacitor charges up slowly. So it's doing what we think it's supposed to be doing. However, if we were to view the spectral view, ooh, I suspect we are going to have problems there with aliasing and general nasties. So what we will do is sweep the capacitor value as we go through the file, and I know electronically that you can't get variable capacitors of 1 microfarad, but in software we can. Excellent. So we now need to rerun it. There we go. Reload it into here. And that doesn't look good from a spectral point of view. Now we go to here. Right. So, look at that. Yep, it's still doing what we think it is, but if we play it, well, that's strange. We're getting a strange stepping effect in the frequency, and if we view the spectral view, ugh, lots of nasties happening. That should all be smooth, and what these things are and all this rubbish, that's not good. And the reason it is doing that is because we are only switching at whole samples when we're switching from high to low, and if we look at the discharge, once we get up here, it's only a few samples, so every time it's jumping, that is we're going up, so it'll be one fewer sample on the down, on the discharge cycle. So, as I expected, this is not going to work for us because we're getting all sorts of problems with switching suddenly on a sample, or switching suddenly in digital audio. So we are going to have to think of something different. And because this video is going on soon, we will finish this video here and save that for the next video. So for now, it's goodbye from Triplicate. Goodbye.